All right, so let's look at the next topic is I'm using Blundell here, okay, but putting my own spin on things. The first thing is not in Blundell; it's actually something the geometric interpretation. So let's talk about exact and inexact differentials. Okay. Right. So suppose we have an infinitesimal quantity which is a function, which is of this form. So I'm kind of making up this notation, but so we have some function f1 of it. Hang on. Yeah, we have some function f1 of x and y times dx, and some other function f2 of x and y times dy. And the idea is that this thing is small because it's multiplying dx and dy. These f1 and f2, even if they're finite, they don't have to be infinitesimal. The result is small because you have this infinitesimal quantities multiplying them. Okay? So this is a general differential. So this differential is an exact differential. Delta f is an exact, sorry, my cat is meowing, is an exact differential if there exists a function, let's call it f of x and y, such that delta f is d of f. Okay, so if such a function exists, then this is an exact differential. In other words, if f1 of x and y is equal to del of f of del of x of y, and if f2 x and y is equal to del f by del y of x. So that's when we can say del f is an exact differential, okay? If you cannot find such a function, then delta f is an inexact differential, okay? Right. So if our differential is exact, then we have some nice properties. So if delta f is equal to d of f, then if we integrate delta f from some point to another point, so say f at x0, y0 to f at x1 to y1, because this is just d of f by the, what is it called, the fundamental theorem of calculus or something? We have f of x1, y1 minus f of x0, y0, which is saying that the value of these functions do not depend on the path in which we got to that value, right? So they, this function only depends on the position of that. So for exact differential, then it follows that if you do a path integral over a closed path, it is 0. Now, if I can convert this into the language of vectors, so I can think of delta f as a vector, right? So I'm defining delta f to be f1 times, say, dxi plus f2 dy of j, right? So if I do this over some path, closed path d of s, then let me just draw the picture. So suppose this is my xy plane and this is the path. Then Stoke's theorem tells us that this is equal to the surface integral of the curl of this vector delta f dotted with the area, right? And this is 0. So this is 0. This guy is 0 only when this is 0. So that means that for exact differential, curl of delta of f, this thing is 0. Okay. Sorry, I made a mistake here. This should be f, and there shouldn't be these things. Okay. Okay. Is that clear? Why we have this? We're just using Stoke's theorem here. Let me write that down. So here, this equality comes from Stoke's theorem. Okay. So a little bit of a story. Stokes was Maxwell's teacher in Cambridge. So apparently Stokes had discovered this theorem, but he had not published it. But he put it as a math tripos problem, as an exam problem. And only Maxwell was the student who could solve it. Okay. So Stokes' theorem tells me that if for exact differential, if we make a vector f out of these functions which go into making this exact differential, remember that for exact differential, this is nothing but d of f, d of x, y, right? And this is nothing but d of f, d of y at x, right? Then if I make a vector out of these guys, then its curl is 0. Now we can write out what the curl of f is, and you know that this is going to give you the following identity: del f del y is going to be equal to del f2 del x, right? This is what the curl, each component of this curl is going to be this. And now if I express f1 and f2, then we see that delta f of y, delta x is equal to del squared f, del x, del y, which is what Nahi was talking about. Okay? So I don't know if this is a geometric interpretation, but this gives you some sort of interpretation, right? It gives you something to think about, Nahi?
Yes, sir, I think so. I never thought it like this. Yeah.
Right. So I didn't either until I read Blood Bowl. All right. So Okay, any questions?
Sir, I have a comment to make on this. Like,
Yeah.
the way that I intuitively get like the double differential equality is that like in that vector field, going in one direction and then in the other is the same thing as going in the first direction, in the second direction and then in the first. You don't
Yeah, yeah.
accumulate different rates of change based on which direction you choose to go first.
Yeah, it's that is one way. Yeah, you're right. And it's kind of I think it's kind of a in some sense
So the basic problem is it's quite easy to visualize first derivatives, but when we do second derivatives, it kind of becomes hard to visualize it. I guess
I think what Saif is
like it's not just
trying
slope or something.
right. I think what Saif is trying to say that there is a in when you learn differential geometry, did you take GR anyway? By any of you?
No, but
When
I
you
studied a little bit of tensor calculus on my own.
right, so you know that there you have stuff like the commutator of covariant derivatives acting on some tensors, and that is for general space times, and for that's not zero. Even for fat space time, this is not zero. This because hang on, do I want to say that? No, for flat space and that is zero. Yeah. So it's so these are not quite derivatives. They are covariant derivatives, but I think what Saif is trying to say is that if I think of these guys as some sort of vectors, which you can, then what he's saying is that if I go in that direction first and that direction first, that is the same thing as going in this direction and this direction. Okay, you can make these things more precise. So if I were to like go down the route that Saif is trying to say, I would have to actually introduce some notions of differential geometry. So which is probably going to be a little bit too far in this class. Okay, so but Nahi, just a note that you might want to look into some differential geometric textbook. There's an introductory textbook by so it's not SHC, it's SCHUTZ,